Okay, so wave revision, be able to draw a label diagram of a wave, state the relationship between frequency and period, know what the energy of a wave depends on, know the three characteristic behaviours of a wave. So draw the diagram like that there and label it in as many parts as you can think of, and I've done one of them for you.
Okay.
Just call him Cupcake. Do you know what comes after Cupcake? Too many cupcakes. So that's what she's actually saying.
That's
right.
Fat.
Okay, labeling the diagram. This is what we have so far. You've got wavelength measured in meters. You could also measure the wavelength between a few different points. You could measure the wavelength between the two tops of the wave here. That could be wavelength as well. So that is lambda. And you could also measure lambda from here to here. That could also be lambda. Lambda is the length of one complete wave. Where it starts. Okay. From crest to crest, from trough to trough, or from crossover to crossover, as long as it's one complete wave. And while we're on that, this bit here is the crest of the wave. This would also be a crest here. Label this diagram if you don't have it. This is a trough. Okay, so that's lambda and that's crests and troughs. We also have to have amplitude. Amplitude is the height of the wave. It's from the centre to the top. We're given the symbol small a. There to there, that's A. And there to there, that's A as well. A equals amplitude. Now, we're not going to put a unit next to amplitude because it's more of a property of a wave. The amplitude of a wave depends on what type of wave it is. Depends how much energy it has. The waves have energy, sea waves have energy. The higher the amplitude, the more energy they have. Voltage waves, radio waves all have energy as well, but it's not measured in meters. It's measured in how strong the voltage is or how strong the electric wave is in a radio wave. So amplitude is a measure of how much energy the wave has. And finally, period, T equals period. Now, however you decide to do it, and that's measured in seconds, and that equals the length of time for one complete wave. So, time for one wave is the period. So that would be the time on the board would be from, say, here to here. That time on the time axis would be the period. Okay? And that's just about all the stuff we need to remember about waves and what waves are. Now, waves also have a speed that we can use. Ross, were you going to ask?
Is the period the length of one wave?
Not the length of time for one wave. The length of one wave is the wavelength.
So like from your start point to like the
From my start point to there,
excellent.
on that axis would be the time. If you measure the time, that would be from there to there, that would be the period. Okay? Right, so let's just summarise a couple of those things I've just said. First one is the amplitude is how big, how high the wave is and how much energy it has. So the energy of the wave depends on the amplitude of the wave. So things to note are the energy, let's down underneath, of the wave depends on the amplitude. So high amplitude means high energy. Low amplitude means not a lot of energy. And the best way to think about it is just think of water waves. The higher the wave in terms of water, the more power it has, the more energy it has to knock you over to sink ships, etc.
Would it be the other way around? Amplitude depends on energy.
Well, if you were to say how much energy does that wave have, you look at the amplitude and say, well, it's high amplitude, so therefore it's high energy.
Right, okay.
Yep. Yeah, that's fine. Okay, so amplitude, the energy wave depends on the amplitude. We know that the period equals the time for one complete wave, but the period also equals 1 over frequency. Now we did this when we were trying to work out the frequency from my oscilloscope. The period's 1 over frequency to get that. They would have another thing we need to think about in terms of our. So, be able to draw the label diagram of a wave. That's just what we've done. State relationship between frequency and period. We've done that. Know what the energy of a wave depends on. Well, the amplitude. This last bit here. Know the three characteristic behaviours of a wave. So, Ross, can you give me one characteristic? What one thing a wave must have and must be able to do? Ross.
Ross.
Can you tell me one thing a wave must be able to do? A wave must be able to do three things you know of from telecoms and health topics. We did the standard game. A wave can do three things.
Go up.
Go up? No. Think of a light wave or a radio wave.
Go through things.
Go through things. Yep. So what happens when a wave goes through things like glass? Light refracts. It refracts. So that is a wave. So for something to be a wave,
Is it for this in our actual notes?
what?
Is this
Some of it is, not all of it.
Right.
For this to be a wave, it must do three things. It must, one, refract. That's called refraction. So that is refraction. That's the first thing. The second thing it must do, so refraction is one. Let's get three things it must do. Jay, give me another one.
Diffract.
Diffract, yep. What is a diffraction? Now, if refraction is the wave bending as it goes between materials. So if you go from air to glass, the light will bend. If it bends, it's refracting. It's bending as it goes between one material and another. Now you need to go and revise that if you can't remember. And what is diffraction then, Jay?
Moving around an object.
Bending around an object. So if it comes to a building, the wave will bend round it. It comes to a hill, the radio waves will bend down it. If you've got light coming in through a window, the light bends round the window frame to get into the whole room. Okay, the light can bend, radio waves can bend. That's what diffraction is. And the last one, probably the easiest one, is what? Yeah, I know you know. Hands never touching the ceiling. Robert, can you tell me? Hands up when you go to a mirror. Can you tell me? How should you look in a mirror?
Wait till you have to read.
Reflect. Light reflects. So, last one is reflect.
Okay, Tom, stop shaking the table.
Okay, stop shaking the table on purpose. Right, so it must refract, diffract, and reflect. If it cannot do one of those three things, then it's not a wave. There's one more of these it must be able to do, and that's what we're going to learn now. And it's called interfere. Interference. Okay? Why are you all smiling? Interference. So
what's refraction?
Pardon? Very good. Right, so the fourth property of a wave is interference. Or not? Interference. So that is the fourth property of a wave. We've done reflection, refraction, diffraction, and you have interference. If a wave can interfere with each other, then they are a wave. Radio waves can interfere with one another, light waves can interfere with one another, sound waves can interfere with one another. So this is what we're going to do in terms of interference. And I'm going to give you a very brief description of what interference is. I'm going to show you on the board, it's really easy. And then we're going to draw what's known as an interference pattern. Okay, so let me draw my waves on the screen. Right, these are both coming from different sources, different speakers, different radio transmitters. Okay, now what can you tell me about these waves? Just by looking at them, Ross. Now, by the same, we need to have the same what, Carson?
The same wavelength.
And amplitude and period and frequency. Basically, same wavelength and same frequency. Now, if these waves have the same wavelength and the same frequency, we say these waves are coherent. Coherent means that they are the same as each other. So these are coherent waves. Now, interference can only occur from coherent waves, where they have the same... Oh, no, that's not true. Interference can happen from any types of waves, but the type of interference we're going to look at just now can only happen from coherent waves. Now, these are coherent, which means they are both the same. They're both the same frequency and the same amplitude. Can we all look at the board? It's important. They're both the same frequency and the same amplitude. If I take this wave and I move it around a little bit, and I say, okay, at this point here, now these waves interact with one another. That wave is interacting with that wave there. If I was to put these two waves together, like that, okay, they came together like that. There were sound waves, for example. What would happen to where these waves crossed over one another? You get something, say, now remember the height of the wave is how much energy it has. So if you have a 10 decibel sound added onto another 10 decibel sound, what happens to the wave, Ross? 20 decibels. You can add the energy of these waves together, and that's called constructive interference.
Does that not increase the amplitude?
Pardon?
Does that not have to increase the amplitude?
It will increase the amplitude. So the resultant wave the amplitude would increase. Right?
So
If I
double it.
it would double it. Well, if the waves are coherent, it would double it.
Yeah.
Right? Michael, please stop doodling in the front of your notes and look at the board. Jay, I don't know what you're doing, but put your pen down and look at the board just now.
Copying away.
Well, I didn't ask you to do that just now. I want you to pay attention first before we do this. So if you've got these waves in line, then they will line up one another, and the troughs and the crests will meet one another, and they will constructively interfere with one another, allowing the amplitude to double for the crests and the troughs. Now that would be constructive interference. If I move these, now just out of interest, if I move it this far, by how much have I moved them if I move them that far? How far have I moved them in terms of wavelengths? Half. Well done, Ross. I've moved it a half wavelength ahead. So that's a half wavelength ahead. If I had it another half wavelength ahead, it would get to there. Another half wavelength ahead, I would get to there, and then there, then there, then there. So if I take this wave and push it forward by one half a wavelength, I get to there. Another half wavelength, I get to there, and so on. So if I add it on one half a wavelength, there. Now, what can you tell me about what's happening to, say this is a sound again, what happens to the sound at this point here? Look at what you've got here. You've got one, remember the wavelengths are positive and negative. That's going to be going up by a certain positive, and this wave is down by a certain negative. What will it sound like, Andrew Brown? What will that wave sound like, sound wave here? If you've got a positive and a negative part, without reading the notes. Don't know. Take a positive part of a wave, say it's positive 5, and put it together with a wave that's negative 5. Dylan, what are you going to get? Positive 5, add negative 5. Nothing. 0. You get 0. And that's called destructive interference, where they completely and utterly destroy each other. Now you can see it happening here as well. Look, at this point here, it's destructive interference, destructive, destructive. That's all zeros. And at these points in between, the positive cancels out the negative, and you get destructive interference. So if the wavelength goes half ahead, then it's destructive interference. If it goes one full wavelength ahead, then it goes back to being constructive interference again. So you can just look at that this way. We'll take this red one out again and move it around a bit more. So and get a second then. Is it going to join together?
Press back loads of times.
There we go. Right, so take the red one again. That's constructive, half ahead, destructive. Half ahead, constructive. Another half wavelength ahead is destructive, half wavelength ahead, constructive. Now obviously the wavelengths over to the right, they are not lining up properly. But if these waves are in phase with one another, then they will cause constructive interference where they line up, and they'll cause destructive interference where they don't line up. They're actually exactly half a wave out. Now what we have also happening is maybe the waves don't exactly line up with one another, half a wavelength or a full wavelength. Say they're slightly out, say I get to there and I put it there. You're still going to get constructive and destructive interference, but it's not going to be totally constructive or totally destructive. It's going to be somewhere in between. You're going to get like a composite, you're going to get like all these numbers adding up. So at this point here, you're going to get whatever the value of this is, plus the value of that one, added together. Right? So let's summarise a few bits for that. Now, you're talking about total constructive and total destructive interference for these things to happen. Right, let's have a look. So what we've got here is you've got two waves and they are what's called coherent. Coherent means that they are both the same. They have the same frequency and the same wavelength. They don't have to have the same amplitude. So, take two waves that have same frequency and wavelength. Sorry? You don't have to. I just want you to take these two just now. You don't have to draw a diagram just now. They do not need the same amplitude. And what we say is they are coherent. They are called coherent. Coherent means they have the same wavelength and the same frequency. And that's a word we have to remember. Coherent waves. Coherent. It's in your notes on page 3. Coherent waves. So for normal unrelated wave sources, the effects will be complicated and difficult to predict. If the sources are coherent, which is what we're going to do here, it's possible to generate subtle wave patterns or interference patterns. So you can get interference from any combination of waves, but to get a completely constructive interference or a completely destructive interference, you need to have them coherent. Same wavelength, same frequency. Right?
They are called coherent waves.
They are called coherent waves, yeah? Is that other one? Coherent waves. Okay? Right. So what we're going to draw now is we're going to draw an interference pattern. We're going to come back to this idea of coherent waves and constructive and destructive interference. So I'll give you a little note on this next day once we get an interference pattern drawn.
Is there an easier way to draw it?
You're just going to do what you're told, right? So you're going to take a piece of A4 paper, and so the A4 paper will look like this. And what you're going to do is you're going to create two sources on the bottom. You're going to have, now it doesn't really matter how far apart you put them, as long as you kind of don't put them, take the middle of the page and then put them in the other half of the page, so there's in the middle of one of the halves of the page. And what you're going to do is you're going to draw the waves that come out from that source. Now, you don't have to draw the troughs of the wave, you only have to draw the crests of the wave, which means you can draw semicircles based upon the wavelength of the wave. So you can draw semicircles coming out of each source, like that. No, so this is going to be from this source here, source 1. So source 1 will have all these waves coming out. You must make sure that you increase the size of the compasses when you do this the same each time. So say the wavelength of the wave is 1 centimetre, then you must have the first wave is going to be 1 centimetre away from the source, the second one is going to be 2 centimetres away, 3 centimetres, 4 centimetres, and all the way up. You get as many as you can onto the piece of paper. You're then going to do the same for the other wave. Now it's got to be the same wavelength, so you can do again 1 centimetre, 2 centimetres, 3 centimetres, 4, etc. all the way up. And you can do that in pencil, to do that and kind of create your diagram this way. Once you've finished that, I would like you to take the points where the lines cross and mark an X. Now I want you to do that in colour. So there's coloured pencils here, there's traffic light pencils here, you can do that in red. So just do the first one in standard pencil. You can do, I want you to cross everywhere where the lines cross. So everywhere you see a line crossing, I want you to put a red cross using the coloured pencils. What is it?
Do we do each lot of lines from different source and different colours?
No, you can just do them in pencil. Just do them in pencil. Just pencil that, but the wavelength must be the same. You won't get a diagram like this, you'll get one that looks better than this. And everywhere where the lines cross, I want you to put a red cross on your piece of paper. Now, everywhere where there is a exactly halfway between the lines, so for example, this is a line, and this is halfway between this line, I want you to put a blue circle. So you're going to put a blue circle where you find the waves are half a wavelength out. So there is one wavelength between here and here, in the red, but you're halfway on the blue. It's on the wavelength of the blue, but halfway between the red. So you get a blue circle there. You'd also get a blue circle here, a blue circle here, and one here.
Between the reds.
You'd also get a blue circle here, here, and here. Now I want you to put all the blue circles in and all the red crosses. Alright? And then you should have that finished. I want you to finish that tomorrow in class. It'll take you a while to get it done. And then when you come in on Monday, we'll bring a diagram and we'll complete your diagram and we'll talk about path difference and interference patterns. So you can start that in class just now. You can get your idea of it. You can ask me some questions and then you can finish it off tomorrow with some questions from your sheets.